Welcome to this second introductory lecture on proof techniques. In this first segment, we're going to motivate the need for extra proof techniques above and beyond the ones we already studied in the previous lecture. And so, to motivate these new proof techniques, let's consider the following theorem. It says, for every integer n, if n squared is even, then n is even. The first thing before you start writing a proof is to analyze the form of the theorem. This theorem is a universally quantified conditional. So the four proof techniques we studied in the previous lecture all apply. So let's consider them in order, considering the easiest ones first. The first proof technique we studied was the vacuous proof. Remember, the vacuous proof of a conditional P implies Q applies whenever we can prove that the hypothesis P is always false. So here the hypothesis is that n squared is even, when clearly that's not always false if n is any integer. Therefore, this proof technique is not applicable in this case. So let's turn to the second proof technique called the trivial proof. And remember, the trivial proof of a conditional P implies Q only applies when Q, that is, the conclusion of the conditional, is always true. Here the conclusion is n is even. We're not going to be able to prove that that's always true. Therefore, the second proof technique also does not apply here. Okay, so let's take the next possible proof technique for a conditional P implies Q, which is the direct proof. Well, this one doesn't have any particular assumptions about the truth values of the hypothesis or the conclusion of the conditional, so it's definitely applicable here. Remember, the general technique here is to assume that the hypothesis P is true and to conclude that the conclusion Q must also be true under this assumption. But first, remember that we're really using the direct proof for quantified statements, since we have a universally quantified theorem here. So let n be an arbitrary integer, and don't forget at the end of the proof to use universal generalization. But for now, we're just going to prove that P implies Q for a particular but unknown or arbitrary integer n. Let's assume the hypothesis of the conditional, namely that n squared is even. And from there, we must prove that n is also even. So the only statement we have to start from is this one. So we're going to use the definition of even to infer that there must exist an integer k such that n squared is equal to 2 times k. But what do we do now? This is where we currently are in the proof. And let's not forget our goal, which is to prove this proposition. So when you get stuck in a proof, it's always a good idea to look at the goal and try to reason backwards. If we want to prove that n is even, we can simply use the definition of being even. And what that tells us is that we're trying to write n as the product of 2 and an integer. Since we already have an expression from n squared, all we need to find is a way to transform this expression to get to an expression for n. So it's not very hard here. How do you go from n squared to n? Well, you just divide by n. So the next step here we're going to perform is to divide both sides of the equality by n. N squared divided by n is n, and the right-hand side becomes 2k over n. Since we're trying to write n as a multiple of 2, we're going to separate the 2 and write n as 2 times the number k over n. So now we can apply existential generalization to infer that there is a k such that n is equal to 2 times k. And k is this number here. in this particular case. But wait a second, that is the definition of n being even, right there. So the next step is to infer that n is even, which is the conclusion of the conditional here. But we're not quite done, because remember, n in this proof is not all integers. It's a specific but unknown or arbitrary integer. In order to prove the original theorem, which was universally quantified, we must not forget to apply the universal generalization rule to go from an arbitrary integer to all the integers. So the next step is to conclude that because n was arbitrary and we didn't make any other assumptions about n throughout the proof, it must be the case that for all integers n, if n squared is even, then n is even, which concludes the proof. Now, before you turn it in for grading, what's my usual advice? That's right, you better double check your proof. In fact, I guarantee you that this proof is incorrect. So I'll give you a minute to pause the video and find the error or errors in this proof. Did you get it? Okay, here is the first error. When we're going from this step to this step, we got to be very careful because we're dividing by n. And what's the one thing you must always watch out when you're dividing by a number? That's right, you must make sure that number is not 0. But actually, n could be 0 because n is an arbitrary integer and 0 is an integer. So this step of dividing by 0 is not a valid step in a proof. It could break down because 2k over 0 is not defined. Fortunately, there's a way to fix this. We could split the proof into two cases. Either n equals 0 or n is not. If n is not, then the proof carries over as written down here. If n is 0, then it's okay, we can make a special case and plug in 0 here and to realize that 0 is even, 0 squared is 0, so in which case both the hypothesis and the conclusion are true, and therefore the conditional is also true in that case. Still, this error is something to watch out for, so you're not allowed to infer from this that this is true because you can never divide by a number that could be 0. Now, let's say we fix that problem as I just indicated, and let's say now we're doing the case where n is not 0, so this step is allowed. I still claim that there is a big problem here. So I'll let you think about it and come back to me when you saw the mistake. So you got it? The problem is in these two lines here. How did we go from this line to this line? Well, we applied the definition of being even. But the one thing that you always keep in mind, even though we don't write it on the slide, I say it every time, is that k must be an integer. But what is the particular value of k here in the proof? Is that number k over n. That is, this k is different, is the integer that comes from here. So we know that this k is an integer and this n is also an integer. However, it is not guaranteed that k over n is an integer. It could be a fractional number, a rational number that's not an integer. Therefore, it is not allowed to infer from this step to this step that k is an integer, and therefore you cannot infer that n is even. That step is also broken. Now, there might be ways to fix it, but it's not going to be easy. So the conclusion of this segment is to show that in this case a direct proof is actually not trivial. Let's just say that we don't know how to fix it, so we can't use the method of direct proof to prove this theorem. And that is therefore a motivation to introduce new proof techniques which are much easier and will be applicable to this theorem.